Hello everyone, and welcome back to this channel to this video. So as I said in the last video, in this one, this time we're going to go through this paper called Optimal Policies Tend to Seek Power." It's actually quite the title itself is quite catchy and very interesting. Uh, so we'll go through that paper. Again, welcome back to this channel. Welcome back to this series, in which we are going to research on building morally conscious AI. Uh, we're going to write the paper on that. So yeah, I think let me just upload the paper so that you could. I'll just show you the paper. The one, that one. Yeah. So this is the paper. I'll just open it. So this is the paper. Software policies tend to seek power. Right. So let's read the abstract first. So some researchers speculate that intelligent reinforcement learning agents would be incentivized to seek resources and power in pursuit of the objectives we specify for them. Right. So other researchers point out that RL agents need not have human-like power-seeking instincts. To clarify this discussion, we developed the first formal theory of the statistical tendencies of optimal policies in the context of Markov decision process. Sorry for that. Okay. Process, we prove that certain environmental symmetries are sufficient for optimal policies to tend to seek power over the environment. These symmetries exist in many environments in which the agents can be shut down or destroyed. We prove that this environment most reward functions make it optimal to seek power by keeping a range of options available and maximizing average reward by navigating towards larger sets of potential terminal states. So yeah, so given a process, given a let's say objective, in optimal policies, an optimal policy tries to gain maximal power or maximal options, right? In this paper also they come to the definition that more power and power is defined as having more uh, options or accommodating let's say many options, right? Or that is what power means. That's how power is described here in this paper, which is actually quite natural, right? Maybe it's not maybe it's not human type of power, human instincts, because well, probably not. But desire is also can also be narrated as something that desire is also can be narrated as a tendency, right? Even a tendency is considered a desire. So maybe this tendency is not like the desire that like in the context of humans, but maybe just having the tendency to seek more resources, right? Maybe that is power. That is having. I'm just speculating that. And we'll read the introduction now. Or should we like maybe we could summarize all this, or what? Let's just read it. Let's just read the introduction, and then we will decide whether we should read everything or use ChatGPT to summarize everything. So yeah, introduction. So these people, Omohundro, Bostrom, Russell, hypothesize that highly intelligent agents tend to seek power in pursuit of their goals. Such power-seeking agents, one second. Such power-seeking agents might gain power over humans. Marvin Minsky imagined that an agent tasked with proving the Riemann hypothesis might rationally turn the planet along with everyone on it into computational resources. However, another possibility is that such concerns simply arise from anthropomorphization of AI systems. Anthropomorphization refers to, you know, considering people as human or God, or spiritualizing things, or I say, assuming that they have a specific soul and they're like humans. So, sometimes we assume AI as human, right? Assume AI to have tendencies of humans or features of the human. That's called anthropomorphization. Anthropomorphization. All right. So some argue that it's just mere anthropomorphization. No real thing that like that exists where AI, rationally not try to take control over humans. But again, seeing more resources, I don't think a specific, uh, an agent with human features is necessary to just seek more resources to solve problems. Again, we'll go through this paper. Let's see what they say, right? So we clarify this discussion by ground in a claim that highly intelligent agents will tend to seek power. In section 4, we identify optimal policies as a reasonable formalization of highly intelligent agents. Optimal policies tend to take an action when the action is optimal for most reward functions. We expect future work to translate our theory from optimal policies to learned real-world policies. Section 5 defines power as the ability to achieve a wide range of goals. Okay, for example, money is power, and money is instrumentally useful for many goals. Conversely, it is harder to pursue most goals when physically restrained, and so a physically restrained person has a little power. An action seeks power if it leads to states where the agent has higher power. So, achieving wide range of goals, okay, interesting. So, having many options to do things, or let's say for example, in the human case, let's say your objective is to be happy, then well, maybe uh, you know money you can have many options, so you have many options to achieve your objective. So in this case too, to achieve the objective, right, the more options you have to achieve the objective, or the more resources you have to achieve the objective, well then you are considered powerful, right? That is what this is. That is what I think, that is what this is. Again, we are not long into this paper, right? We have just started. So let's see what we have. Is this the second page? That I Yeah, probably. Yeah, first two. We make no claims about when large scale AI power seeking behavior could become plausible. Instead, we consider the theoretical consequences of optimal action in an MDPs. MDP, Markov decision process. Section 6 shows that power seeking tendencies arise not from anthropomorphism, but from certain graphical symmetries present in many MDPs. These symmetries automatically occur in many environments where the agent can be shut down or destroyed, yielding broad applicability of our main result. Interesting. So related work, let's just read this small portion. Let's see what it is. So an action is instrumental to an objective when it helps achieve that objective. Okay. Some actions are instrumental to a range of objectives, making them convergently instrumental. The claim that power seeking is convergently instrumental is an instance of the instrumental convergence thesis. Instance of the instrumental convergence thesis. Several instrumental values can be identified which are convergent in the sense that their attainment would increase the chances of the agent's goal being realized for a wide range of final goals and a wide range of situations, implying that these instrumental values are likely to be pursued by a broad spectrum of which situated intelligent agents. Several instrumental values can be identified which are convergent in the sense that their attainment would increase the chances of the agent's goal being realized for a wide range of final goals and wide range of situations, implying that these instrumental values are likely to be pursued by broad spectrum of situations. Right, simple, right? So, uh, you know, let's say if some let's say some objective or some instrument or some values, uh, well, if they make the model achieve many goals, wide range of goals, then they are considered instrumental, right? I think that is what's specified here. Anyway, for example, in Atari games, avoiding virtual death is instrumental for both completing the game and for optimizing curiosity. Optimizing curiosity. Okay. Optimizing curiosity. I don't know what Atari. Okay. All right. So okay. So yeah. Why do you not die? You say in the game. Well, you have to finish. You want to finish the game. Well, win the game, and also optimizing curiosity. I don't know what that means, but anyway, many AI alignment researchers hypothesize that hypothesize that most advanced AI agents will have concerning instrumental incentives such as resisting deactivation and acquiring resources. May and AI element researchers hypothesize that most advanced AI agents will have concerning. Okay, very interesting topic, right? Uh, okay, so they even AI agents, I think they do not want deactivation like deletion, right? So that this is one thing that this is one narrative that is widely propagated, especially let's say 5 years before, where if AI gets powerful, we have to like shut it down, but then it tries to like resist deactivation, right? It tries to like acquire power on its own and you know control the on and off button, right? Many books and let's say movies, right? Uh, that is also shown here because to finish their objective, right? Their objective is the only thing that they want to solve, right? Uh, if you are aware of the loss function, right? We have the loss function in AI while doing neural networks. So they want to achieve the least loss function and, as possible, as much as possible. So then, that is the only objective. That is their only desire, let's say in human sense, right? And in order to achieve it, they'll do anything, such as resist deactivation, which is stopping, and a lot of things, right? So that is what powerful means. Having wide amount of resources to solve their particular objective or problem, or we formalize power as the ability to achieve wide variety of goals. Okay, Apatic said demonstrates that our formulation returns intuitive verdicts in situations where information theoretical empowerment does not. Okay. Some of our results relate the form and power of the states with structure of the environment. Foster and Diane, Drummond, Sutton, and all these people note that value functions encode important information about the environment as they capture agents' ability to achieve different goals. Value functions encode important information about the environment. Okay. Turner speculate that a state's of optimal value strongly correlates strongly across reward functions. In particular, these people learn regularities across value functions, suggesting that some states are valuable for many different reward functions. Okay. Okay. So we are assuming that we have like many reward functions, which is actually quite interesting, and that is what we need. When building like more general AI, um, either states optimal value correlates strongly across reward functions. Regularities occur value functions, suggesting that some states are valuable for many reward functions. That is powerful. Okay. Meanings identify navigate towards convergently instrumental bottleneck states. We are not the first to study convergence of behavior form of function. In economics, turnpike theory studies of certain paths of accumulation tend to be optimal. In a biology, convergent evolution occurs when similar features independently evolve in different time periods. Lastly, computer vision networks reliably learn edge detectors implying that these features are useful for a range of tasks. Okay, so identifying things and using them for a range of tasks, or maybe I was wrong. Maybe more resources is not a very good definition. Maybe achieving range of tasks, right? Let's say we have multiple reward functions, right? Multiple reward functions to optimize multiple categories of uh, behavior or behavior representation by these many reward functions. So the more reward functions we could have to optimize in a state, the more powerful the being is. Uh, Very interesting. Okay, so that is the related work. Now let's get to the third part, which is state visit distributed functions quantify the agent's available option. Okay. So let's see what this figure is. I have no idea. So L uh, down arrow, can I say that? L down arrow is a one cycle, and phi is a terminal state, or is that theta? No, that is phi, I think. Arrows represent deterministic transitions induced by taking some actions. Since the right subgraph contains a copy of the left subgraph, proposition 6.9 will prove that more reward functions have optimal policies which go right than which go in left at state star, and that such policies seek power, both intuitive and reasonable common sense. We clarify the power seeking discussion by providing what optimal policies usually look like in a given environment. Okay. We illustrate our results with a simple case study before explaining how to resolve. Okay. Let's see what this is. This is a page 3, right? Page 3, yeah. Okay. This list WP theory contributions of independent interest supporting the list. Okay. Definition 3.1. SAT is a rewardless MDP with finite states. So we have some definitions. Okay. I don't think. Okay. Okay. So like this is like what are they trying to prove? We have no idea. Okay. So we have. Let's see what is the conclusion, because we don't not need all this. For our research, maybe we don't have to read all this, but okay, let's see. About a wide, okay, definition 3.1, rewardless MTP. Okay, we find six action spaces as a day and stochastic transition function. Okay, we have a stochastic transition function that takes in S and A and gives us a delta S. So I think S is okay. Okay, so the state is S and the action is A, and we have a transition function in which the action A is no, the action is takes place in the state S, and then we'll get the new delta S. So we did the discount rate y. So what's that? Gamma, I think, as a variable with domain 101. Okay, I don't understand what discount rate is. Uh, okay, so we have definition 3. This is rewardless MDP, where there is no reward. Well, we are computing the state or the action, but then what is T? Okay, so T is a stochastic transfer function. Sorry, and then I have all right. So maybe we don't like have to like see all this definitions and formulations. We only need the final conclusions. Uh, so I think for now, I think this video, I think we could end it here. And the next video, I'll try to go through this paper and see what the conclusion is, what they try to conclude. I think they're just trying to prove that well, they just try to see more resources or more options. Well, in the case of many reward functions, they try to you know maximize the achievability of many reward functions or optimizing of many reward functions. I think that's what that readable. But anyway, in the next video, I'll go through this paper in more detailed manner, and I'll come up with important, let's say, points that we could consider for our paper, right? Just to include in the paper. So I think for now, let's. I'm going to finish it up now, and I'll see you in the next video. If you are interested, I'll post the paper in the description. So please study if you are interested. Thank you for watching. I'll see you in the next one.